Welcome to the TOEFL Listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good afternoon, Dr. Morales. I wanted to talk about carbon sequestration methods for my seminar. I read about a few approaches, but I am confused about how natural and artificial methods compare.
Hi, James. That is a big but important topic. Let us start by distinguishing natural sequestration from engineered or artificial approaches. Natural methods store carbon in ecosystems or soils. Artificial methods use technology to capture and store carbon, often underground or in products.
Could you give some concrete examples of natural methods first?
Sure. Classic examples are afforestation and reforestation, where trees remove CO2 through photosynthesis and store carbon in biomass in soils. Wetland restoration and peatland conservation are also crucial because these environments accumulate and lock up large amounts of carbon over centuries. Blue carbon is another category that refers to coastal ecosystems like mangroves, seagrass meadows, and salt marshes that sequester carbon efficiently in sediments.
I have heard of biochar as well. Where does that fit?
Biochar is an interesting hybrid. It is produced by thermally decomposing biomass in low oxygen conditions and then adding the charcoal to soils. That stabilizes carbon for decades to centuries and often improves soil fertility and water retention. So it is a nature-based solution that is assisted by a processing step.
What about artificial methods? I know about direct air capture, but not much else.
Artificial methods include direct air capture, where machines capture CO2 directly from ambient air. Captured CO2 can be compressed and injected into geological formations for long-term storage. There is also carbon mineralization, where CO2 reacts with certain rocks to form stable carbonates. Enhanced weathering is related. It involves spreading finely ground silicate rocks on land or in the ocean to accelerate natural rock weathering, which consumes CO2.
Could you give real-world examples of those engineered approaches?
Yes. A good case is Carbfix in Iceland. There they dissolve CO2 in water and inject it into basaltic rock. The CO2 reacts with the minerals and becomes carbonate minerals within a few years. That shows how mineralization can be quite rapid and permanent in the right geology. Another example is Climeworks, which operates direct air capture facilities in partnership with storage projects. And BECCS stands for bioenergy, with carbon capture and storage. That combines biomass combustion to produce energy with capture of the CO2 and geological storage, leading to net negative emissions if managed correctly.
I remember reading that ocean fertilization was proposed to increase phytoplankton uptake. Is that still considered viable?
Ocean fertilization has been widely discussed, but it is controversial. Adding iron or other nutrients can stimulate phytoplankton growth and draw down CO2, but the ecological side effects are uncertain. It can alter food webs and cause oxygen depletion in deep waters. Legal and ethical concerns also limit its deployment. Most scientists urge caution and call for rigorous small-scale trials with strong monitoring before any large-scale application.
What are the main trade-offs between natural and artificial sequestration?
Natural solutions often provide co-benefits, such as biodiversity conservation, watershed protection, and livelihoods. They are generally less energy-intensive and cheaper per ton of carbon removed. But they may be vulnerable to disturbance, for example, fires, disease, or land use change, which can reverse storage. Artificial methods can offer more permanence and controllability, especially geological storage and mineralization, but they are usually more energy intensive and costly, and need careful monitoring to prevent leaks.
You mentioned monitoring. How do researchers verify that carbon stays stored?
Verification depends on the method. For ecosystems, we use remote sensing to track vegetation and biomass changes, and field measurements like soil cores and eddy covariance towers to quantify fluxes. For geological storage and mineralization, we use subsurface monitoring tools, seismic surveys, tracer tests, pressure measurements, and sometimes isotopic analysis. Combining methods improves confidence about permanence and helps detect leakage early.
Are there standards for permanence and accounting for these methods?
There are emerging frameworks. Permanence is often expressed as the probability of retention over a specific time frame, for example, 100 years or longer. Life cycle analysis is used to account for emissions associated with capture, transport, and storage. For example, direct air capture needs energy, and that energy source affects the net benefit. Certification schemes try to include leakage risk measurement, monitoring, verification, and social safeguards.
How do we decide which methods to prioritize?
Prioritization should consider cost-effectiveness, scalability, co-benefits, environmental risks, and social acceptance. In many places, protecting and restoring natural carbon sinks is urgent and cost-effective. At the same time, we need engineered removal like direct air capture and mineralization for hard-to-abate residual emissions and to meet ambitious net negative targets. A portfolio approach is necessary.
What about social impacts and equity? For instance, could BECCS compete with food production?
That is an important concern. Large-scale bioenergy demand can compete with food land and biodiversity if not planned carefully. Sustainable biomass sourcing is essential. Community engagement is also critical for siting storage facilities and restoration projects. Many communities depend on lands that might be proposed for afforestation, so policies must balance climate goals with local needs.
If I include technical vocabulary in my seminar, what terms should I define for the audience?
Define terms like sequestration, carbon sink, carbon stock, flux, permanence, mineralization, direct air capture, BECCS, enhanced weathering, and blue carbon. Also explain monitoring techniques such as eddy covariance, remote sensing, and isotopic analysis. Giving short examples like CarbFix for mineralization and mangrove restoration for blue carbon will help the audience connect concepts to practice.
That is helpful. One last question. Are there promising new technologies or synergies between methods?
Yes. Integrating biochar into agricultural practices while restoring wetlands is promising because it enhances soil carbon and reduces pressure to convert natural ecosystems. Coupling direct air capture with sustainable geothermal or renewable energy reduces its emissions intensity. Enhanced rock weathering could be combined with agricultural amendments to improve soil health while sequestering carbon. The key is to match methods to local ecological and social contexts.
Thank you, Dr. Morales. I think I can structure my seminar around those comparisons examples and the monitoring and social aspects.
That sounds like a solid plan. If you want, I can review your slides before the seminar and suggest any clarifications.
I would appreciate that. I will email a draft by next week.
Good. I look forward to it. Remember to emphasize both the potentials and limitations of each sequestration method.
Listen again to part of the conversation, then answer the question.
A good case is Carbfix in Iceland. There they dissolve CO2 in water and inject it into basaltic rock. The CO2 reacts with the minerals and becomes carbonate minerals within a few years.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit Spinta.org.